Hi, welcome to the Mentored Engineer. In this video, we're going to look at our 3-pin calculators and how to use them. All right, so let's go to the website, www.mentoredengineer.com, and then we're going to do a search for pin calculator. Okay, so when you do the search, you're going to have 3 calculators come up, and these generally get most of your pin loading cases. This first one here is pin with 2 unequal loads, and that would be used for something like a crane base pivot, where you have a boom sticking out and you've got your force from the cylinder pushing it up, and then you're looking at the elbow and you can move it side to side. So maybe you have the force that's reacting the cylinder and holding the load, and then maybe you got a little bit of side load from wind, or actually just a side load pulling on the cable. So you have that. So this would be a great calculator for that. The next one is a pin loaded in double shear, and this is just a pulling force, and then it's got 2 ears to hold it so that the pin has 2 shear locations. And then the last one is a simple pin loaded in single shear. And that's probably the simplest case. Let's start there just to see how this works. All right, so here I'm going to pick a force, and let's just say it's 2,000 pounds, and I have a 1-inch diameter pin, and you scroll up here, I have T1 here, and let's just say that is 1/2 inch thick, and T2 is 3/8 inch thick, and the gap between them, and generally with a single shear pin I want to keep this very small, so I'm going to say it's 0.0625, that's a 1/16 of an inch, and I'll just say I'm using a 100 KSI pin. I'll go ahead and enter that, and looking down here I have the load on my pin, and this is the highest shear stress that it has. It's got an equivalent area of this, and therefore a stress of 2,500 psi. I can look at both bearing areas, and this is the stress where the pin fits into the hole of the parent material, so this would be T1, and that's a 1/2 inch, and since the pin is 1 inch or 2 inches in diameter, I get that area. Oh, it's a 1-inch pin, 1-inch diameter pin. So I have a 1/2 inch of bearing area, and that's 4,000 psi. For the other plate, it's a little bit thinner, so my stress actually goes up to 26 or 5263. All right, then I'm calculating my section modulus of the pin, the area moment of inertia of the pin, the effective bending length, and that would be from the center of the plate to the next center of the plate plus the gap in between. So that's 1/2 inch. And then my maximum moment based on that gap, or the effective bending length. And here I get my stresses. My normal stress on the pin is 10,000 psi, and then I'm going to combine it with the shear that I calculated up here and get the principal normal stress and the principal shear stress, and then my design factor based on those things. And here I make some notes on the calculator itself, especially this load case, because it's not one that we use a lot in structures, unless of course you're using a bolt or something to hold those 2 plates close together. But it is important to know that you are going to have that moment in there, and one of the plates, at least one of the plates, is going to be taking that full moment load. Okay, so let's move on to the pin loaded in double shear. So you can see here in the diagram, it's got a real good basis here for selecting everything I need. All right, I'm going to go again with my 2,000 pound load, my 1-inch pin. T1 is going to be 1/2 inch, and I will keep T3 as 1/2 inch as well. but I will make this one 1.5 inches, the middle beefy one. And I can actually put in an offset as far as where the load is compared to the overall width of that. You can see I've got it offset here as well. And I'm going to put that in as 0.25. Oops, not 25. And then I can put my gaps in on each side. So I'm just going to make those 1/8 of an inch. And I'm going to have 100 KSI, whoops, not 1,000, 100 KSI pin as well. All right, we can go back and we're going to find similar results, similar format. All right, so I've got my maximum pin shear, the area of the pin, and therefore the stress. I'm going to find the bearing area on T1, T2, and T3. And you can see that T1 and T2 are different because of the offset load that I applied in that. Section modulus of the pin here, area moment of inertia, the effective bending length, and the maximum moment. Now here our moment is just a little bit less than it was in the previous example. All right, so we have our normal stress from bending, and then we're going to add that in, normal stress plus our shear stress, and we come up with our design factors here. So the last load here is a pin that is loaded with two unequal loads. And I used the crane earlier as an example of this, where your main pivot pin would have a load on it that reacts to the force, and then the reaction from the cylinder as well. And then you'd also have like a side load that would essentially act as a couple, pulling on one side and pushing on the other. So what we're going to do here is go to our pin with two unequal load calculators here, and we're going to look at our picture and insert our forces. And I'm going to say my first force is 4,000 pounds and my second one is -500 pounds. And I can do that. Negative numbers are awesome. And I have a 1-inch pin. The thickness of the one plate is, I'm going to say 0.5 inches. Thickness of plate number 2, I'm going to say 0.75, 0.75 again, and 0.5 for T4. The width in between my plates, I'm going to say that's 12 inches. And the gap on each side, I'm going to say is 1/4 inch. You know, we don't want things too tight when you're trying to assemble this. And then 100,000 KSI pin. All right, so let us go down here and we'll hit calculate. Fill our inputs. All right, so here we got similar form as the other two calculators. We've got our shear force, our shear area, and our shear stress. And since we have two shear forces, it will find the maximum one of the two and put that out. Which just so happens to be between T1 and T2. All right, so here we can see our stresses on those plates, and because the load on the other side is at -500 pounds, my stresses are much lower over here. Once again, calculating the section modulus, area moment of inertia, effective bending length, and then the moment at each of the reactions, which is where the maximum would be. It would be one of those two. And you can see here that T2 would be the highest loaded one. So that's where we get our normal stress from. And then it's going to add in our shear stress and our principal stress. So this pin, maybe a little bit under designed for what I would like. All right, well that's basically it for this calculator. I hope you can use it. Hope that these three calculators will help you speed up your engineering work quite a bit. Thank you for using our calculator. Bye-bye.